Welcome to this problem walkthrough. In this session, we'll explore problem number 1575, titled Count All Possible Routes. We'll break down the problem requirements, examine the brute force approach, and analyze its complexities. Let's dive in and get started. In this problem, we are tasked with determining the total number of distinct routes you can take from a starting city to a destination city, under certain constraints. You are given an array called locations, where each element represents the position of a city on a one-dimensional line. Along with this, you are provided three integers: start, which is the index of the city where your journey begins; finish, the index of the city where the journey must end; and fuel, which represents the total amount of fuel available for the trip. The goal is to calculate all possible routes from start to finish, such that the fuel used along the way is sufficient for each step. A route is considered valid if you can travel between the cities using the available fuel, even if it involves revisiting cities multiple times, including the starting city. However, the route must ultimately end at the finished city. For every liter of fuel consumed, you can travel a distance of 1 unit, and the distance between two cities is calculated as the absolute difference of their positions. Since the number of valid routes can be very large, the answer should be returned modulo 10 to the power of 9 plus 7. The fuel, represented by an integer, can range from 0 to 200. Our output will be a single integer indicating the total number of valid routes from start to finish, with the result being modulo 10 to the power of 9 plus 7. Let's look at an example to better understand the problem. Imagine we have the locations array as 2, 3, 6, 8, 4, with start set to 1, finish set to 3, and fuel set to 5. In this case, the starting city is at position 3, the destination city is at position 8, and we have 5 liters of fuel available for the journey. Our goal is to calculate how many different ways we can travel from city 1 to city 3 while adhering to the fuel constraints. Now, let's discuss the explanation for this example. We begin at city 1, which corresponds to position 3, and aim to reach city 3, located at position 8. With 5 units of fuel, there are exactly 4 valid routes. First, we could take a direct route from city 1 to city 3, consuming exactly 5 units of fuel. Second, we could travel from city 1 to city 2, which is at position 6, using 3 units of fuel, and then continue to city 3 using 2 more units of fuel. A third route involves traveling from city 1 to city 4, which is at position 4, using 1 unit of fuel, and then from city 4 to city 3, consuming an additional 4 units of fuel. The fourth route is a bit longer, where we go from city 1 to city 4 using 1 unit of fuel, return to city 1 using another unit, and then proceed to city 3 using 5 units of fuel. These 4 routes collectively account for all possible ways to travel from city 1 to city 3 with the given fuel. Let's consider another example. Suppose locations is 4, 3, 1, with start set to 1, finish set to 0, and fuel set to 6. Here, we start at city 1, which is at position 3, and aim to reach city 0, located at position 4. With 6 units of fuel, there are a total of 5 valid routes. The first route is a direct trip from city 1 to city 0, which requires just 1 unit of fuel. A second route involves traveling from city 1 to city 2, which is at position 1, using 2 units of fuel, and then from city 2 to city 0, consuming 3 additional units of fuel. Another route involves traveling from city 1 to city 2, returning to city 1, and then proceeding to city 0. Similarly, we can also travel from city 1 to city 0, return to city 1, and then go back to city 0 again. Finally, a longer route involves traveling from city 1 to city 0, then to city 2, back to city 1, and finally to city 0. These account for all 5 possible routes. To summarize the constraints and edge cases for the problem, all values in the locations array are distinct, ensuring no 2 cities share the same position. The indices start and finish must be valid within the range of the array, and the fuel value must be between 0 and 200. Some important edge cases to consider include scenarios where the locations array has only 1 city, in which case the only route is to stay at the city if start equals finish. If the fuel is insufficient to cover the distance between start and finish, no routes are possible. On the other hand, if the fuel is exactly enough to cover the distance, there will be precisely 1 valid route. Additionally, with large values in the locations array, up to 10 to the power of 9, we must ensure that calculations do not result in overflow. Lastly, revisiting cities multiple times might be necessary in some cases to optimize fuel usage and achieve the destination efficiently. To tackle this problem, we first considered a brute force approach. The intuition here is straightforward. We explore all possible routes between the start and finish cities while accounting for the fuel available. At each city, we attempt to travel to every other city, deducting the fuel required for each trip. If the fuel runs out, that path is terminated, and if we reach the finished city, we count that route as valid. However, this approach quickly becomes computationally expensive. Since each city has up to n possible next moves, and we explore all paths recursively, the number of recursive calls grows exponentially. This results in an infeasible solution for larger inputs, as the time complexity is O, n caret fuel. Additionally, the space complexity is O, fuel, primarily due to the recursion stack. Clearly, while this approach is intuitive, it is not practical for larger scale problems due to its inefficiency. To address these issues, we refined the brute force approach using dynamic programming with memoization. The dynamic programming approach optimizes the brute force method by avoiding redundant computations. Here, we define a state as a pair, city, fuel, representing the number of ways to reach the finished city starting from a specific city with a given amount of fuel remaining. Using memoization, we store results for previously computed states, significantly reducing redundant calculations. The state transition involves exploring all possible moves from the current city to other cities where the fuel cost is within the available fuel. For each valid move, we recursively update the route count and store the result in a DP table. The base cases are straightforward. If the fuel left becomes negative, no route is possible, so we return 0, and if we are already at the finished city, we add 1 to the route count. The key insight here is recognizing that the problem involves overlapping subproblems, where the same city, fuel, state may be revisited multiple times. By storing intermediate results, we reduce the time complexity to O, n squared asterisk fuel, which is a significant improvement. The space complexity for this approach is O, n asterisk fuel, accounting for the DP table. For further optimization, a rolling DP array can be used to reduce space complexity to O, fuel, but it introduces additional complexity in implementation, making it less intuitive. After evaluating the options, we chose to implement the dynamic programming approach with memoization as it strikes the best balance between clarity and efficiency. This method avoids the exponential recursion of the brute force approach, making it practical for larger inputs. It is also easier to implement and debug compared to the space-optimized DP variant, as the rolling DP adds unnecessary complexity for most use cases. While the space-optimized DP reduces memory usage, the trade-off in implementation complexity does not justify it for this problem. By leveraging memoization, we achieve a solution that is both scalable and intuitive. This makes it particularly well-suited for competitive programming scenarios, where both performance and ease of implementation are critical. Thus, the chosen strategy ensures that the solution is robust, efficient, and easy to extend if needed. In this problem, the goal is to calculate the number of valid routes between a starting city and a destination city, under a fuel constraint. Each city is represented by its position, and traveling between cities consumes a specific amount of fuel based on the distance between them. The challenge lies in ensuring that the fuel never goes negative while counting all possible routes that satisfy the constraints. To begin analyzing the problem, the input consists of the positions of the cities, a starting city, a destination city, and the total available fuel. The output is the total number of valid routes that meet these requirements. A straightforward brute force approach involves recursively exploring all possible paths. We start at the initial city, deducting fuel based on the distance to each possible destination. If the remaining fuel becomes negative, the path is terminated. Otherwise, we recursively try all further transitions from the current city. The base case for this approach occurs when the remaining fuel is 0 or there are no valid transitions left to explore. However, this brute force solution quickly becomes inefficient for larger inputs due to exponential time complexity. To address the inefficiency of the brute force approach, we introduce optimization using memoization. The brute force method has overlapping subproblems, such as repeatedly calculating paths from the same city with the same fuel level. Memoization helps avoid redundant calculations by storing results for each city and remaining fuel in a dictionary or a two-dimensional array. The recursive relation is defined as follows. Let dp, city, fuel, represent the number of valid routes starting from a given city with a specific amount of fuel. For each possible next city, if the remaining fuel is greater than or equal to the distance to that city, we add the result of dp, next underscore city, fuel distance, city, next underscore city, to the current dp, city, fuel. Additionally, if the current city is the destination, we always add one valid route to account for the case where no further movement is needed. The base cases include setting dp, city, fuel, to 0 when the fuel is negative and initializing dp, destination, fuel, to 1 for all valid fuel levels. With memoization, we eliminate redundant computations and significantly improve efficiency. An alternative to the recursive approach is to use an iterative, bottom-up method to construct the dp table. In this approach, we systematically fill the table for all cities and fuel levels, starting from base cases and building up the solution. The final result is then stored in dp, start, total underscore fuel, which gives the total number of valid routes modulo a constant mod to prevent overflow. This formulation highlights some important insights about the problem. First, it relies on recursive decomposition, where the problem is broken into smaller subproblems by considering transitions between cities. Second, overlapping subproblems exist, and memoization is critical for avoiding redundant computations. Third, the fuel constraint naturally limits the number of possible paths. Finally, modulo arithmetic ensures that the computation remains efficient even when the number of routes becomes large. The key data structures include a two-dimensional dp table, where dp, city, fuel, records the number of routes from a specific city with a given fuel level, and an adjacency matrix or a distance function to quickly determine the fuel cost between cities. To ensure efficient computation, we use a modulo constant, such as 10 to the power of 9 plus 7, for all operations to handle large numbers. When analyzing the time complexity, the brute force approach is extremely inefficient, with a complexity of O(n), as it explores all possible paths exhaustively. In contrast, the optimized dynamic programming solution has a time complexity of O(n*f*(n), where n is the number of cities and f is the total fuel available. This accounts for iterating over all cities, fuel levels, and possible transitions. The space complexity is O(n*f) for the dp table and O(n) for the recursion stack in the memoized solution. It's also important to consider edge cases. For instance, there may be no valid routes if the starting city is isolated or the fuel is insufficient to reach any other city. Another edge case involves exact fuel usage, where transitions need to work even when the fuel is reduced to 0. Finally, proper handling of modulo arithmetic ensures that results are computed correctly without overflow errors. To solidify our understanding, let's walk through an example. Suppose we have 3 cities located at positions 0, 2, 4, with the start city at position 0, the destination city at position 2, and a total fuel of 4. We initialize the dp table by setting dp, 2, f, equals 1 for all fuel levels f equals 0, as reaching the destination with any fuel count is a valid route by definition. Next, we fill the dp table iteratively for each city and fuel level, calculating transitions to other cities based on the fuel cost. For each transition, we check if the remaining fuel is sufficient, and if so, we update the dp table accordingly. The final result is stored in dp, 0, 4% mod, representing the total number of valid routes starting from city 0 with 4 units of fuel. This approach ensures that all routes are computed efficiently while adhering to the problem's constraints. Here, we begin implementing the solution by defining a solution class with a CountRoutes method. This method takes in the list of locations, the starting city, the finishing city, and the available fuel. We also define a constant mod set to 10 to the power of 9 plus 7 to ensure our results fit within the required constraints by taking modulo operations later. Next, we calculate the number of cities, n, based on the length of the locations list. To optimize our solution, we use a memoization table dp, which is a 2D list initialized with -1. This table will store the results of subproblems to avoid redundant calculations. The core of the solution is a nested function DFS that performs depth-first search. It takes the current city and the remaining fuel as arguments. Inside the DFS function, we first check if the remaining fuel is negative. If it is, this means it's not possible to continue the route from here, so we return 0. Next, we look at the memoization table. If the result for the current city and remaining fuel has already been computed, we return the cached result. Otherwise, we initialize a variable count to store the number of valid routes. If the current city is the finished city, we start by counting this as one valid route. Finally, we iterate through all other cities to explore possible moves. For each potential destination, we calculate the fuel cost as the absolute difference in locations between the current city and the next city. If moving to the next city is feasible given the remaining fuel, we recursively call DFS for the next city with the updated fuel and add the result to our count. To ensure our count doesn't exceed the modulo limit, we take the modulo mod after each addition. Once the exploration of all possible routes from the current city is complete, we store the computed result in the memoization table DP for the current city and remaining fuel. This ensures that if we revisit the same state, we can directly return the stored result without recalculating. Finally, we return the computed count for the current city and remaining fuel. After defining the DFS function, we initiate the depth-first search from the starting city with the given initial fuel by calling DFS start fuel. The return value of this function call will be the total number of valid routes from the start city to the finish city, considering all possible paths and fuel constraints. This approach efficiently uses dynamic programming with memoization to avoid redundant calculations, ensuring the solution works within the constraints of the problem. Here, we start by defining the class and importing the necessary utilities. At the core, we declare a constant mod to perform modulo operations, ensuring that our results remain within bounds for large numbers. The main method, countRoutes, accepts an array of locations, the starting and finishing cities, and the available fuel. We initialize a 2D array, DP, to store the results of subproblems, with dimensions based on the number of cities and the fuel capacity. Each cell in the DP table is initially set to -1, indicating that the state has not yet been computed. The computation relies on a helper method, DFS, which is defined as a recursive function with memoization. This allows us to explore all possible routes efficiently while avoiding redundant calculations. The DFS method begins by checking if the remaining fuel is negative, in which case no route is possible, and we return 0. If the state has already been computed, we simply return the memoized value from the DP table. If the state is not memoized, we initialize the count of routes. If the current city matches the finished city, we increment the count by 1, as this represents a valid route. Next, we iterate over all possible cities. For any city other than the current one, we calculate the fuel cost as the absolute difference between the current and next city locations. We then recursively call DFS for the next city, reducing the fuel by the calculated cost. The result of this recursive call is added to the count, and we take the modulo operation to ensure the result stays within the defined bounds. Finally, we memoize the computed count for the current state in the DP table to reuse later and return the count. This approach ensures that we explore all valid routes efficiently while leveraging memoization to optimize performance. Here, we start with a basic example to understand the problem. We are given locations 2, 3, 6, 8, 4, a starting city at index 1, a finishing city at index 3, and an initial fuel of 5. To solve this, we use a depth-first search (DFS) approach combined with memoization. First, we initialize a constant mod to handle large numbers, and determine the number of cities, n, which is 5 in this case. We also set up a memoization table DP with dimensions n by fuel plus 1, all initialized to -1. The DFS function is invoked starting from city 1 with the full fuel amount of 5. Since the starting city is not the finished city, we initialize a variable count to 0 to begin tracking valid routes. Now, the DFS function begins exploring potential next cities from city 1. For the first option, city 0, the fuel cost is calculated as the absolute difference between their locations, which is 1. With 4 units of fuel remaining, the function calls DFS for city 0. At city 0, the count is initially 0, and further exploration continues. However, returning to city 1 is avoided to prevent backtracking. Next, city 2 is explored, but the fuel cost of 4 leaves no remaining fuel for further steps, resulting in 0 valid routes from city 0. The result for this state is memoized as dp 0, 4 equals 0. Returning to city 1, the function then considers city 3, which is the finished city. The fuel cost of 5 exactly matches the available fuel, so we reach the finished city. Here, count is incremented by 1, and the result is memoized as dp 3 0 equals 1. The total valid routes originating from city 1 with 5 fuel is now 1, which is memoized as dp 1 5 equals 1 and returned. In this larger example, we analyze a scenario with more fuel. The locations are 1, 2, 3, starting at city 0, finishing at city 2, and with 40 units of fuel. As before, we initialize mod 4 large numbers, determine the number of cities n is 3, and set up the memoization table dp. The DFS begins at city 0 with 40 fuel. Since city 0 is not the finished city, we start with a count of 0 to track valid routes. From here, the function explores possible next cities to determine how the fuel can be utilized to reach the destination. From city 0, the DFS function first explores city 1, where the fuel cost is 1. With 39 fuel remaining, DFS is called for city 1. At city 1, the count is again initialized to 0, and further exploration continues. Moving to city 2, the fuel cost is another 1, leaving 38 fuel. At city 2, we reach the finished city, so count is increment to 1. This result is memoized as dp 1 39 equals 1 and returned. Back at city 0, the result is memoized as dp 0 40 equals 1 and returned as well. The final output for this example is 1, indicating one valid route to the finished city with the given fuel. In this example, we examine a case with multiple routes. The locations are 1, 3, 6, 10, starting at city 0, finishing at city 3, and with a fuel reserve of 10. After initializing the variables, the DFS begins at city 0 with the full fuel. From city 0, the function explores different next cities. For instance, traveling to city 1 consumes 2 fuel, leaving 8, while traveling to city 2 consumes 5 fuel, leaving 4. From each of these cities, further recursive exploration is performed, uncovering multiple paths that lead to city 3. At each step, the memoization table is used to avoid redundant calculations and store results for states defined by the current city and remaining fuel. Ultimately, the total number of valid routes to the finished city is found to be 4, demonstrating the efficiency of this approach in handling multiple paths. This problem highlights the importance of combining DFS with memoization to efficiently solve complex route counting problems. The memoization table ensures that redundant calculations are avoided by storing results for each unique state defined by the current city and the remaining fuel. Meanwhile, the DFS explores all valid paths, summing up the results for those that reach the finished city. Additionally, the modulo operation ensures that the results stay within the bounds of large integers, making the solution robust and scalable. Together, these techniques provide a systematic way to count all possible routes under the given constraints. The time complexity of our solution is primarily influenced by the DFS function and the memoization table. To break it down, consider the number of states in the DP table. The table has dimensions nx, fuel plus 1, where n is the number of cities and fuel plus 1 represents all possible fuel levels, including 0. This gives us a total of n asterisk, fuel plus 1, states. For each of these states, the DFS function explores all other cities, meaning there can be up to n1 recursive calls per state. Furthermore, the work done within each state involves iterating over all n cities, where each operation, such as calculating distances or making recursive calls, is an O(1) operation. As a result, the work per state is O(n). Given that there are n asterisk, fuel plus 1, states and each state requires O(n) work, the total time complexity becomes O(n asterisk, fuel plus 1 asterisk n). Simplifying this, we get O(n squared asterisk fuel). This is the overall time complexity of the solution. Now, moving to space complexity, the solution requires space for the memoization table, which has dimensions nx, fuel plus 1. This contributes O(n asterisk fuel) space. Additionally, the recursive call stack can go as deep as n in the worst case, where the DFS might traverse all cities sequentially. Each recursive call uses constant space, leading to an O(n) space requirement for the call stack. On top of the memoization table and the recursion stack, the algorithm uses a few auxiliary variables, such as count and fuel_cost, which require a constant amount of space. This adds O1 to the space complexity. Combining all these factors, the total space complexity is the sum of the memoization table and the recursion stack, which simplifies to O, n asterisk fuel plus n. Since the first term dominates, the overall space complexity is O, n asterisk fuel. To compare, a brute force approach would attempt to explore all possible routes from the start city to the finish city without memoization. For each city, it would consider all possible transitions and track all possible fuel levels. This results in an exponential number of routes, approximately n, in the worst case. Additionally, tracking fuel usage adds another layer of complexity. The time complexity for this naive approach would therefore be around O, n asterisk fuel. In contrast, the optimized approach leverages memoization to compute each state, city, remaining underscore fuel, only once, drastically reducing redundant calculations. This optimization brings the time complexity down to O, n squared asterisk fuel, which is significantly more efficient than the brute force alternative. In terms of best, average, and worst case scenarios, the algorithm consistently explores the n asterisk fuel plus 1 states, so the time complexity remains O, n squared asterisk fuel, regardless of the input. This consistency arises because the complexity depends solely on the size of the input and not on specific patterns within the input. Mathematically, the big O proof aligns with our analysis, with n asterisk fuel plus 1 total states in each state requiring O, n work. The total computation is O, n asterisk fuel plus 1 asterisk n, which simplifies to O, n squared asterisk fuel. Memoization ensures no state is recomputed, and the recursion depth remains bounded by the number of cities, confirming the correctness of these bounds. When tackling this problem, there are some common mistakes that can trip up even experienced coders. First, it's essential to account for edge cases within the constraints. For instance, you might overlook scenarios where the input array is empty, or there's only one city in the problem. Neglecting these can lead to runtime errors or incorrect outputs during testing. Another frequent pitfall is attempting a brute force approach for large inputs. If you try all possible routes without pruning invalid paths, the resulting exponential time complexity quickly becomes infeasible, especially for scenarios where the number of cities exceeds 1,000. Mismanaging fuel constraints is another issue. This could involve not properly handling fuel recharges or subtracting fuel incorrectly during transitions, which directly impacts the accuracy of your path calculations. Lastly, overcomplicating the implementation can create unnecessary challenges. Writing overly complex recursive functions or relying on too many global variables makes debugging harder and increases the likelihood of logical errors, so simplicity and clarity are key here. Another critical mistake to avoid is failing to optimize overlapping subproblems. Often, recursive solutions involve repeated calculations, and if you neglect to use memoization or dynamic programming, the time complexity can balloon significantly. Now, when you're in an interview setting, there are a few best practices to keep in mind. Always start by understanding the problem constraints thoroughly. These constraints often provide valuable hints about which approach, like dynamic programming or a greedy algorithm, might be most effective. Additionally, if you initially propose a brute force solution, it's vital to immediately discuss its trade-offs and then pivot to optimizations like pruning or memoization. Make sure to articulate edge cases clearly. This demonstrates that you're thinking comprehensively and leaves a strong impression on the interviewer. Finally, prioritize writing clear and maintainable code. Instead of trying to impress with overly clever solutions, focus on explaining your logic step by step in a way that's easy to follow. To build a deeper understanding, it's helpful to explore related problems that share similar patterns. For example, LeetCode 1463, Cherry Pickup 2, involves optimizing paths with constraints, much like the current problem. LeetCode 871, Minimum Number of Refueling Stops, focuses on managing fuel efficiently, which aligns closely with the challenge here. Similarly, LeetCode 64, Minimum Path Sum, and LeetCode 174, Dungeon Game, both involve dynamic programming approaches to navigate paths while minimizing or optimizing resource usage. Beyond related problems, you can also consider alternative approaches to solving this type of question. Dynamic programming is particularly effective for problems with overlapping subproblems, although it may come with higher space complexity. A greedy approach offers faster implementation and lower space usage but can fail in scenarios requiring global optimization. Lastly, graph-based search techniques like DFS or BFS are useful for exploring all possible paths, though they require careful management of cycles and visited states. Each approach has its trade-offs, so the choice depends on the problem's specific constraints and requirements. Great job! In this session, we broke down the count all possible routes problem, explored the brute force solution, and discussed its implications. Remember, brute force is often the first step to uncover insights for optimized approaches. Thank you for watching, and see you in the next walkthrough. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!